Hi, thank you for joining me. My name is Ellie Bublick. I'll be discussing the AI Deep Learning with Big Data final project for the ADTA 5550 course at the University of North Texas this fall 2021. Let's get started. A little bit about me so you have some background. My name is Ellie Bublick. I'm a senior manager of analytics at Dentsu International, where I primarily work with marketing analytics data. I have a background in marketing analytics and strategy and research and IT, primarily with nonprofits. I'm interested in forecasting with AI and data visualization, and below are a couple reports where I was a co author. And pretty soon I will be an author again with the 2021 SP Salary Survey Report that should be coming out publicly pretty soon. Um, yeah, it's been a joy getting to learn some of these applications in this course, and I'm excited to talk to you about them today. So let's get into the agenda. I will cover a data set of images which would lend well to a CNN application, how to get a hold of the CIFAR-10 data set, building and training and testing a CNN on the CIFAR-10 data, comparing it with a different CNN I have worked with, as well as improving its performance. So there are many data sets out there now, publicly available to many, and artificial intelligence has been used for many applications where identifying the contents of an image is really helpful. An application many people use without thinking about it is to unlock their phones with their image of their face. That's known as Face ID on Apple iPhones. And people do it all day long without even thinking about it. So that's a good example of a application of a convolution neural network, a CNN, as I'll refer to it. So part of the assignment was to look for a data set of images where you could build a CNN. So one I found through the University of Massachusetts at Amherst is called Labeled Faces in the Wild. It is publicly available. I will be sharing links to my professor with where to access it, and it comes ready and prepared for being used for deep learning applications. There are images of 13. There are 13,000 images of more than 5,000 people, and they are pre-labeled. So when you would come across Deborah Messing, who is the photo here in the bottom middle, you would be able to um, train the model with the existing labels and have it figure out how accurate it is getting as it goes along. And you can download the data from the University of Massachusetts, but it's also available natively in Python by importing the 51 package. So, moving into one of the convolutional neural networks I'll be discussing is the CIFAR-10 dataset. It is a large dataset of 60,000 images. And for many, that may not sound like a lot of data. I mean, 60,000 records to many does not seem like very much, but you'll want to also remember that when you're dealing with image data, you're dealing with every pixel in that image. And the images in this file come in the size of 32 by 32 pixels. So you have that element combined with these are pictures in color. So there are, you would multiply 32 by 32 times 3 to see how many data points there are just in one image. And I'll get into that a little bit later, where that kind of rears its head down the line. But just so you're aware, the data set comes prepared with data split between training and testing images, and there are five randomly selected training subsets, so you can have a lot of flexibility to work with this data given this sort of preparation being done for you. And the images are labeled already in 10 classifications. So there are dogs, there are cats, there are birds, there are 10 mutually exclusive classes or labels in play in this data set. So that's also something to have in mind when you're programming the output. What should this model spit out when it's done? If it were to just ingest all of these and you were to start feeding these images back to it, then what should you um, tell it to give you when it's done? So, moving on to another data set that we will work with. CIFAR-10 was the first, and I'll have examples of using a neural network with it. MNIST is another one that will come up somewhat down the line. It's a very similar data set in size. It's about 70,000 images. It's a little bit smaller. As you see here, the images a sample of them is shown on the right, and they are of numbers ranging from 0 to 9, which makes up 10 classes, similar to the other data set. But they are in actually grayscale, so like white to black, which is considered only one sort of dimension. So the size of each one of these files is a good bit smaller because you only have to worry about the data being 28 by 28 pixels, and times one leaves you with what you had before. So a little bit smaller of a data set. And let me transition us now into talking about how we are going to get these data sets into an environment where we can use them. Okay, so first we had to download 7 different data files to the local machine, then create a folder with a specific name in order to access it via Jupyter Notebook, um, and then upload it to the remote virtual machine, which is using the Google Cloud platform. So that's sort of an overview of the process of just getting it into the Google Cloud platform. It's not the CIFAR-10 data is one you actually have to sort of have available in this direct fashion, whereas some other data sets you can simply access via code in Python via API or other packages built into the network and environment of Python. So, moving on, let's get into talking about some of the designs of the neural networks. So, CIFAR-10 was the first one I would like to cover since it's going to be the one we'll talk about the most. Um, so over here are an illustration really of what I've done with it, and here are a couple sample images from the CIFAR-10 data set. This is our input. All of these are collated together, and in a convolution layer, information is extracted and then pulled, and then again and again. I've used two of these sort of layers to sort of process all this information because you're talking about a great big quantity of big data here that we'll be working with. So essentially, in this set of duplicated layers of convolution and pooling and convolution and pooling, the the CNN is learning the features of what are in these different files, and then within the pixels within them. And then it has to transition to flattening out all the data from all these pixels, then really, figuring out what goes to what, and seeing, here are the labels I've been given, and output what is the sort of vector of probabilities that this image belongs to one of these classes, and then make the determination, okay, this one to me, as a neural network, seems like a bird, a car, a cat. So this is sort of just a general overview of what this CNN does for us, behind the scenes, so that we can present things like this. With the MNIST data set, I used actually the exact same design. It's a little bit different of a data set. It's in the gray scale here, as you can see, but essentially, other than the data being a little bit different, and maybe some smaller things, the actual design of what what CNN has been used is the exact same. And that's good because we'll use that to be able to compare these two. Okay, so I want to give a little bit more data behind some of the things I had said earlier when I talked about the dimensions and the data and the size differentials. So this is where I want to cover that with you. The MNIST dataset information is here, and CIFAR-10 is below that. And I've got this big call out because CIFAR-10 has actually 3 times more data points in it than the MNIST. But let me walk you through how, sort of that logic to get there and understand that. Oop, sorry, went advanced on accident. Um, so there are 70,000 total images in the MNIST dataset and 60,000 in CFAR10, which is not terribly different. However, um, each image is um, sort of like a record or instance, but within it are all the pixels, and each pixel within it is like a data point. So when you multiply the 28 by 28 to see how many data points there are within just one image, that's 784. And for CFAR10, that is 3,000. So when you then take that next step and say, okay, if there are 784 data points within each image and there are 70,000 images, then you've got almost 55 million data points within the MNIST dataset. And that's rather large. But it gets worse actually when you look at the CFAR 10 dataset and see the 60,000 images have 3,000 data points within them. Then you have to multiply that by 3, because they have an additional dimension of having color. Then you're talking about 184 million data points. And that's a lot of numbers to crunch. That's a lot of data. And it's not always easily handled, as we will see in just a minute. So, just some background in terms of the differences in size of this data. While the number of images is very similar, the pixel numbers are very similar, it's easy to overlook this element and wonder why things may look a little more different than you would expect, which may be some foreshadowing, but I do want to, bring that to your mind so that it's in view when thinking about the things that you'll see. So let's see how these models performed. So um, on the bottom of each of these charts, you'll see an axis called steps. And essentially, it's showing how many steps, how many batches um, the model went through, and what the accuracy level was at that time. So in both, you'll see a similar shape in that, the first few rounds, the accuracy was low, and then it shoots right up, um, and essentially reaches a certain point and tends to stay within that realm. But as you can see on the left, MNIST and its CNN have a nearly perfect accuracy. 99.05% means that this neural network, this CNN, is only wrong um, 0.95 of the time. So less than 1% of the time, the model is wrong, which is pretty good odds. If you have an application that's really important, something you want to be highly accurate with, this one is doing a great job. Um, so that's great. I mean, it's very rare that you can come across um, a model that is so highly accurate. But on the right, you'll see that CIFAR-10 and its convolutional neural network is only 68%, and its trend line is a little bit different than what you're seeing on the left with MNIST. So the CFAR 10 networks trend line, it does go up rather quickly. Within it looks like about 100 um, of the batches, it reaches about 40% accuracy, and then by 1,000 is above the 60% line. But after that, it I don't think at any point crosses the 70% threshold. It flirts with it, as you can see, but it doesn't ever cross that number. So while 68% is the majority, it's most of the time correct. That creates a lot of room for doubt in the minds of who may use that neural network. Any sort of major decisions, I would not recommend using a data set with this level of accuracy um, because you don't want to be wrong, you know, up to um, up to 32% of the time potentially. Um, we can't get everything perfect all the time, but still, to be incorrect nearly 1 in 3 times is quite a large amount. So I don't blame the CNN. It's not its fault. It's us programmers who set it up. So let's see what improvements we can make to help it perform. As you can see, it is attainable to reach a really high level of accuracy, um, but it's not getting there right now. So it needs some help. So there are several options that we can do here. We can add additional layers to the model. I'll remind you what the setup is here. So in the CFAR 10 CNN, we've got two sorts of layers going on. We've got a convolutional layer, the pooling layer. These are kind of standard in the CNN. We could have just done one, but there are two here, and even still, maybe an additional set to have a third convolutional, third pooling layer would help kind of provide more processing, more feature learning of the model. Um, you you tend to only have one flattening layer, but sort of our options here are to increase the number of convolutional and pooling layers as well as increase the number of dense layers. So kind of giving process to the learning side of it is an option, and or either one. It's sort of whatever your flavor of preference. You can also add a dense layer to give it power when it's deciding whether, given all these 18 million data points, what what category best suits the data. Um, it could be a combination that would make a lot of sense. There are lots of ways to do this. People tend to have their own preferences and ways to do things. So there are many options out there, and I might not have chosen one that my classmates had, but I'm curious to see um, what we all did and how it worked. Um, it's been a very busy semester, and short on time, but it it would be interesting to have a little bit more time to play with it and kind of get to know the inner workings of these a little bit more, and really do a deeper analysis of, you know, is this model suffering from not having enough power on the learning side of it, or is it the dense layer side of it? Is it both? I'm definitely curious, but I actually took a different angle. So let me show you what I did. So, per the professor's instructions, the batches we were using were a size of 50. And that is to say to the model, you must take data in batches of 50 images and use that to do your feature learning. And what happens with that, I thought, was this model may not be getting enough diversity of information in order to um, learn the features and what is different among the classes of output values. So essentially, telling it, here's 50 things, figure out what makes them different. I didn't think that that was enough data to do that. You can think of it in the alternative way as well, where, if there were to be 25 random images, is that enough for the model to learn, what a ladybug looks like, what a horse looks like? Does that give it enough information, enough colors, enough shapes to kind of build a pattern within its own framework to identify that this is the general shape it will be and these are some of the colors it will have? I didn't feel that way, so I thought, I could make it smaller and really prove the point if it doesn't go right, but I wanted to try and make the neural network more accurate, so I increased the batch size from 50 to 100 just to see, what impact that would have, you know, because I think a lot of us may be quick to jump to adding an additional layer, whether that be in the feature learning side or the classification side. I was curious to see just what impact the sampling essentially was doing by itself. So on the chart here, you can see the results of what I've done. The first neural network is the darker blue, and the lighter blue is the second network's results. So, as you can see on the right, the first and second are about the same in terms of accuracy. There's not even a full percent difference, but there is sort of a difference when you look at the chart. The light blue shoots up way faster than the second line. They do sort of find a place at, about 1,500 steps, where they do they don't converge, but they get closer and closer, and they hit this point where they almost flatten out, and they don't really start making significant strides anymore in terms of being more accurate. The second neural network flirts with the 70% accuracy line, well more than the first one does. But the graph doesn't tell the whole story. So the graph tells the story of the second CNN is more accurate faster in the learning process than the second one, and ends up a little bit more accurate than the first, but not dramatically. But it doesn't tell a story of what happened when I went and ran these. When I ran the first neural network, it didn't take all that long, maybe a minute or so. But when I ran the second one, it took nearly a half hour, if not more. It was a very noticeable time lag, and it didn't really yield a huge benefit in terms of accuracy at the end of the tunnel, despite my hopes of waiting for it to finish processing and having a better result. So while it does yield a more accurate picture with less steps, which is great because you could probably use less steps since it takes so long to run. It takes so long to run. So, in an environment where you don't want to um, turn something on and leave it running, that may not be the best for your use case. So, kind of like I alluded to earlier, it would be probably a good idea, given this knowledge, to look at the feature learning side of the CNN as well as the um, dense layer side, and experiment with adding additional convolutional layers, pulling layers to the feature learning side, giving it some more ability to learn the 18 million data points. I think that's probably a good idea given this experiment. And then going to the dense layer side if needed, and seeing if that additional help on both ends of the neural network spectrum will help it create a better result. I wouldn't be surprised, and I may even, in my own time, go try it, because I am curious, and I enjoyed it. The assignment I thought was really really interesting, and yeah, there's that's the great thing about this sort of work, is that you've got a lot of flexibility. There are many ways to kind of skin the cat, as some people say. There are many ways to do something. I'll go back to the design so you can kind of look at it in this way. I mean, there are many elements at play here. If you would want to adjust the data size, you can certainly do that. You can adjust these layers. Certainly, you can have many more layers. You don't have to stop at 3. You can have maybe 3, 4, 5, and you can also have more dense layers. Um, there have been times when I used additional layers, and they were really helpful, and sometimes they actually got in the way. So um, there's many ways to do it, and I hope for my classmates that they were able to come up with a better result. And I look forward to seeing their presentations. Thank you guys so much for sticking around and listening to my experience. I hope you had a great time in this semester, great time, as much as you could, listening to my talk. And thank you for your time and have a good one.